Okay, so let me begin. So last time we saw one application of principle of equivalence, okay, which is to derive gravitational redshift. So today we'll discuss another application, which is to understand how electromagnetism works. So you want to understand how electromagnetism works in presence of gravity, right? In other words, when a particle is moving in the presence of gravity and electromagnetism, how should we describe the motion of the particle? So, yes.
You're saying that last example was the fact that
well, the fact that the clock prepared in vacuum works in the same way in the presence of gravity, right? That the fact that the clock in the local inertial frame, right, the clock ticks in the same way, right? That's why you use the principle of equivalence, right? It's somewhat hidden in this derivation, but we implicitly used it, right? Otherwise, it could have happened that in the presence of gravity, will change the dynamics of the clock.
When the clock slows down there.
Yes.
So, I mean, does the redshift provide us a check?
Yes, if the redshift agrees with what gravity, what we predicted, that's a test of principle of equivalence, right? Otherwise, imagine that the gravity slows down the clock, right? That's an extra effect. Then the effect will be different, right?
The precise value of the redshift.
Exactly, will be different now.
Give us an indication how well it matches.
Exactly, right? Because based on principle of equivalence, you can make one prediction of how much the redshift will be, right? And if it doesn't agree with experiment, then that means that you are violating principle of equivalence, right? There is some other effect, right? The clock is slowing down, not just because of principle of equivalence, but because of some additional effects of gravity. Exactly. Okay, are there other questions? Yes. So in the factory, we assume that we are doing it in the same environment, right, which is vacuum, and we make two identical clocks, right? So they run in the same way in the absence of gravity, right? And now we are asking what happens when gravity is present. Yeah. So the fact that even in the presence of gravity, right, the clock will behave as if there is no gravity in the local inertial frame. That's what we used, right? And that's where principle of equivalence entered.
It is just that there is always a choice of frame in which metric will look like and cos.
Yes, and the first derivative of the metric will vanish. Yeah, so that's a mathematical statement. But the fact that in that frame, the dynamics will look identical to that in absence of gravity, right?
It is just that the metric is impossible.
No, it could be, for example, the dynamics could involve the Riemann tensor, right? Okay. We wrote down one example where if such a term was present, right? We wrote down, what did we write? Yeah, that's more relaxed than principle of equivalence, right? Because principle of equivalence we had and we said that suppose this has some d mu r. Okay, let me write this. This is one example. We don't know how to use art, but I am using this now. Okay. So if we have, say, a gravitational field of the Earth, right, of some planet, okay, this quantity is non-zero. Okay, R would have been zero in absence of matter, right? But this is non-zero. Okay, that we will see later. And that means that even in the local inertial frame, right, where gamma is zero and the metric is eta mu, right, you get a non-zero effect, right? And this may be different at different positions, right? So the clock will fill this. Exactly, right? So the effect on the clock will be a function of the position where the clock is, because this depends on where the clock is, right? So the fact that there are such terms are absent is the statement of principle of equivalence, right? Even though such terms are very much consistent with general coordinate invariance, right? We are not violating general coordinate invariance anywhere by adding a term like this. Yes, if principle of equivalence is not true.
Yeah, but we don't have because we have.
Exactly, right? But as I said, this is only an approximate principle, right? These terms we do expect will be there in the full quantum theory, right? But the effects are so small that we don't see them. Yes, it could. I mean, if such terms are there, right, then violation of principle of equivalence. Okay, if you understand the theory very well, then how much principle of equivalence is violated can be used to say what the local curvature is. Yeah, but usually, I mean, we do the other way, right? We try to say, we say the violation of principle of equivalence is a test of presence of such terms, right? To use such terms to actually measure Riemann tensor, there are other ways to measure Riemann tensor, right? Which do not even require this term. Right? But in principle, you are right that if such terms are present, right, then how much principle of equivalence is violated, we'll know about what the Riemann tensor is. Other questions? Okay, so we'll consider electromagnetism. In presence of gravity. Okay. And here there are two aspects of electromagnetism that we want to study. Okay. The first aspect is how electromagnetism affects the motion of a charged particle when gravity is also present. Okay, that's one aspect of electromagnetism. Right? That will generalize the Lorentz force law, for example. The other aspect of electromagnetism is how electromagnetic field is produced in the presence of charged particles. Right? Because both of these are important. You want to know how electromagnetic field affects the motion of a charged particle, but you also want to know how the electromagnetic field is produced in presence of charged particles. And we know both of these in absence of gravity. Right? The first one comes from Lorentz force law. The second one comes from the Maxwell's equations. Okay? And our goal will be to generalize both of these when gravity is present. Okay? And we will follow again the principle of equivalence. Right? We will assume that in a locally inertial frame, the laws should look exactly as it was in the absence of gravity. And we will see that that will tell you what the laws should look like when gravity is present. Is this clear? So let's start from Lorentz force law. Okay. And from now on, we set C equal to 1. Okay, the C was useful when you are trying to test the non-relativistic limit. Okay, but electromagnetism we already understand very well in the relativistic version, right? So you don't have to keep C. We just set C equal to 1. Okay, so this will also avoid various factors, and also we'll use this ESU, right, where all these mu naught and epsilon naught, those things will be absent, right? So we'll just have clean formulae. So let me remind you, okay, this I'm assuming that you have all seen at some point or the other, but let me just remind you that Lorentz covariant formulation of electromagnetism. Okay. Now here I should say that unlike Newton's laws, right, which actually had to be modified in the presence of, because of relativity, in special relativity. Right now we are not talking about gravity. Right? The Newton's laws had to be modified in the presence of because of relativity. Right? But Lorentz, the laws of electromagnetism are in fact valid without any change. Right? You don't have to make relativistic corrections. They are just relativistic. It's just when you first write the Lorentz, the laws of electromagnetism, you may not use a relativistic covariant version, okay, but you don't have to make any changes, right? You can just reformulate in the covariant version. So let me write down the covariant version of the laws of electromagnetism. Okay. So we introduce the vector potential. Mu, okay, which the first component is A0 and then there is a vector. Okay. So this you identified as minus the electrostatic potential. So this is electrostatic potential. And this is what we call magnetic vector potential. Okay, so this phi is related by saying the electromagnetic field, the electric field is minus grad phi. And this is defined by saying that the magnetic field is curl of A. Okay, and maybe I should just say also that we'll also say D equal to 4. Okay, you can do this, of course, in arbitrary dimension, but we'll just do it in 4 dimensions. Okay, so that these are the standard curl and gradient that you are familiar with. Okay. Then in terms of this, one defines field strength. F mu nu. Okay, yes, we will get delta term. So this is in the electrostatic approximation. Okay, so this is in the electrostatic approximation. We'll write down the full expression in a few minutes. Okay, so the field strength is defined but this is just derivative with respect to x mu. Okay. And in terms of these, okay, these are exact formula. EI is just Fi0, which is and this is a familiar formula. This is minus grad phi. So this gives you E as minus grad phi minus the time derivative, right? Because you have set C equal to 1, x naught is the same as time. So this is the usual non-covariant version that we write down. Okay? And B is related. So if Ij is used to define B, so this defines B. But I should have said that I here runs from 1 to 3 and mu runs from 0, 1, 2, 3. Right? That will be the convention. So space coordinate will always denote by the index I. Okay. So if I0 is related to the electric field and if Ij is of course antisymmetric, okay, this is related to the magnetic field by this formula. And this basically translates. So this is Okay, and this basically translates to B equal to curl of A. Okay, that's the way you recover the familiar formula for the electric and magnetic field, okay, in this covariant formulation, covariant version. Is this okay? Are there questions? So using this, we are now going to write down the covariant version of the equation of motion of a charged particle in electromagnetic field background. Okay, so the equation of motion of a charged particle in background electromagnetic field is given by so tau is the proper time. Okay, and this is defined by saying that E is the charge carried by the particle. Is this familiar? Okay, I'll try to show how to get to the standard form of the equations of motion, okay, which may be a little more familiar. To standard form, to get standard form, non-covariant form. We take mu equal to I, okay, which is 1, 2, 3. So then this becomes m dd tau. Okay, let me write it this way. Dx by d tau, the same equation is E. Since I have taken mu equal to I, right, mu has to be j, right, because eta mu nu has no off-diagonal term. So I can write this as eta ij f j rho is clear. We have just ignored the eta I0 term because eta I0 term is 0 anyway. Okay, and eta ij is just delta ij. Is okay. So this side I can write as dd tau of p mu pi. Since pi is dx m dx I d tau. In relativistic mechanics, right? The formula for the momentum, instead of being m dxi dt, the covariant for momentum becomes m dxi d tau. Not even for momentum, the 3 momentum becomes m dxi d tau. So this is given by E. Okay, let's now try to work this out. So because eta I is delta ij, this j is set equal to I. So f I rho, which is E times f I 0 okay. So this is E times EI this is epsilon ij k is clear. I just identify fi0 as ei and fij as epsilon ijk by using that identification. Okay. And now what I'm going to do is to multiply both sides. Multiply by dx0 d tau, which is the same as dt d tau, because I have set c equal to 1. Sorry, you divide by, not multiply by. Essentially, the idea is that you want to go from the tau derivative to t derivative, right? Because the trajectory can be parameterized by tau, but also by t, right? And the usual form is when you parameterize by t. So I just divide by dt d tau. So this becomes dpi dt as E times EI. You see, this goes away. And here dxj d tau, right, divided by dx0 dt d tau is just dxj dt. So that's epsilon ijk dxj dt times dk. And this is the familiar form. The vector form of this is dp dt as E times E plus V cross B, right, where V is dx dt. So this is the usual Lorentz force law, right? The force on a charged particle is the electrostatic force plus the magnetic force, V cross B. Yeah, P is still defined by this, right? So the change that happens is on the Newtonian side, because this part is the Newtonian mechanics, right? Right. So this part has to be changed. Right hand side remains the same. See, because this couldn't have remained the same, right? Because Newton's laws, the classical mechanics changes, right? And the definition of P changes from m dx dt to m dx dt. So that part you have to take into account.
So if we write the Lagrangian, then the kinetic energy will be the relativistic kinetic energy.
Yes, indeed, exactly. Okay, so all this is to convince you that this is really the equation of motion in the covariant form, right? No gravity. Right? Now I am going to use principle of equivalence to demand that in the locally inertial frame, this must be the equation of motion. Okay, and then from there I'll change coordinates and see what we get. What is the form of the equation of motion that we get in a general coordinate system. Yes.
Let me say something these find in terms of so the physics is still the same. For example, is it really telling us something like when you apply a Lorentz force with charge particle, we have a change in momentum. That's a Newtonian wave. So when we define P equal in terms of d by d tau, is the physics really changed? Or is it still telling us that momentum is changing?
Well, the physics does change because when you in Newtonian physics, right? If you apply constant force, the momentum can go to infinity, right? Here it cannot. Well, okay, momentum can go to infinity, speed doesn't go to infinity, right? In a relativistic case, right? And that the fact that it's dp d tau and not dp dt is crucial for that. Sorry, not dp dt. The fact that p is defined as dx d tau instead of dx dt is necessary for that, right? And you can also, I mean, sometimes it's not a correct way to think about this, but sometimes you can think about this by saying that the effective mass of the particle gets increased, right, by this factor, the boost factor, 1 over 1 square to 1 minus v square by c square, right? So as you try to, if you apply constant force, right, the equations remain the same, but because the effective mass is increasing, you cannot accelerate it very fast, right? And that effect, the fact that the effective mass is increasing is essentially this fact that it's m d, okay, the p is m dx d tau and not m dx dt, right? You can replace it by m dx dt, provided m is replaced by some m prime, right, which carries the boost factor. Well, the mass of the particle you think of as fixed as a parameter, right? That shouldn't change. And the mass of the electron, right, is the mass of the electron, right? It's universal constant that is specified. But okay, you can think about it this way, right? As long as you keep that in mind. Any other question? Okay, so now we use principle of equivalence. To conclude that in the local inertial frame, prime. Okay, and let me remind you again, the tau here is a particular affine parameter. It's an affine parameter, but a very special one, right? In which g mu nu or eta mu nu dx mu d tau is just -1, right? Affine parameter is defined by saying that it remains constant, right? But here you are really setting it equal to -1. Okay, otherwise this equation will not make sense, because in affine parameter form we have seen that you can rescale the affine parameter and nothing should change, right? But that's not true here, because there is a second derivative here, there is a first derivative here, right? And that is because we are not allowed to rescale, because tau by definition is when g mu nu dx nu d tau is -1, right? Not an arbitrary constant. Is it clear? Primes are the local inertial frame. For general coordinates, I'll use coordinate without prime. Okay. So the goal is that we start from here and then go to the arbitrary coordinate system. Okay. Now transform this to an arbitrary coordinate system. So let's do it in steps. We write this as m d tau. The dx prime mu d tau, I'll write by chain rule is equal to E times eta mu nu. F prime, we have no idea what it does, right? We keep it F prime for now. So F prime nu rho.
Don't know that. I mean, it should change like a tensor all the time.
How do you know? I mean, so far, whatever you have done, you have not said how to transform a general. We have only talked about how to transform things that are constructed out of G, right? And its derivatives. So you keep it as it is right now. Is that clear? Right? Because if you are formulating this for the first time, right? We only know that principle of equivalence tells us in local inertial frame, it should look like the standard equation, right? Based on that, we have no idea what f prime will become in a general coordinate system, right? That is completely up to us to define, because we have no a priori definition of what f mu nu is in an arbitrary coordinate system. Is that point clear? Right? So we are going to use that freedom, right? The fact that so far nobody has defined what f prime becomes in a general coordinate system, right? Which means we are free to decide how f prime is, what f is, right, in a general coordinate system. Okay, but right now we just keep it f prime. Oh, we are just trying to rewrite this by changing coordinates, right? So changing coordinate just means that x prime we are writing in terms of x, right? I mean, if eta has to change, it has to come from these equations only, right? Because we are just trying to rewrite the original equation in the new coordinate system. Is that clear?
X is our arbitrary coordinate system.
X is our arbitrary coordinate system, right? But we know the equation only in the x prime.
Right.
We are writing x prime in terms of x, that's all. Oh, because eta is just a fixed matrix, right? That's why I have not put any prime. You could have put prime, but it's the same matrix, right? It's not a field, right? It's just diagonal -1, 1, 1, 1. That's all. In card space, exactly. right, in the presence of matrix. So that it takes into account the effect of the gravitational force as well as electromagnetic force. Well, that, I mean, we'll see what happens, right? Right now, what I'm saying is that we have not said anything about what electromagnetic field, right? What is the definition of electromagnetic field in a curved space, right? It's up to us to decide, right? So right now, let's F prime we understand, right? Because in local inertial frame, the laws should remain the same. So F prime is the electromagnetic field that will measure by going to a local inertial frame, right? We know how to measure F prime, right? Let me put it that way. You go to a local inertial frame and measure the electric and magnetic field. From there, you can construct your F prime, right? In a general coordinate system, right? What will you measure to define what the field strength is, right? So since you don't know that, let's just not try to define it right at this time. No, this is F prime of X prime. We are not transforming anything. We are just rewriting the original equation in a new variable, right? So X prime has to be expressed in terms of X, if that's what you mean, right? But otherwise, we are not transforming anything, right? Let me put it. So this should be clear that we have the equation, right, in X prime coordinate system. All we are doing is that we are trying to rewrite that equation in X coordinate system. Okay. So don't think of this as some magic that we are transforming that into something else, right? We are just trying to take the original equation, just change variable, right? That's all.
So why does the eta mu nu not change?
Why does eta mu nu not change? Because eta mu nu is a fixed matrix, right? We are trying to rewrite this equation in the new coordinate system, right?
So we're still not using, like, eta mu nu will like the gravitational field is eta mu nu only in the local inertial frame, right? So that doesn't change to like g mu nu.
Yeah, no. See, that is the only information we have, that the gravitational field is eta mu nu in the local inertial frame, right? And now we are just starting from here. Forget about general coordinate invariance. Forget about everything that we have learned, right? We take this equation and we try to rewrite this in the new coordinate system, right? We don't know what eta mu nu becomes in the new coordinate system, right? Eta mu nu is just a fixed matrix. Let's keep it like that, right? Just changing variables. Fine, we'll try to make eventually everything in one coordinate system, but right now, yes, part of it is one, but X prime is a given function of X, right? We can write in terms of X. Suppose X prime is sin X, right? It will put in some X prime, we'll put sin X in the argument, right? So it's hybrid, it looks hybrid, but it's completely well defined, right? As long as X prime is a given function of X. Arbitrary coordinate system, but who told you that eta mu nu should become g mu nu? Let me ask that, right? We have started with this equation, right? Till somebody tells us that it becomes g mu nu, we have to keep it like that, right? Because otherwise you are changing you are writing a new equation, right? We don't want to write any new equation. Is that clear? I mean, eventually g mu nu will come, but you cannot just put it in. Okay, so this one I'm going to now differentiate once more. So one term will be when this acts on the, okay, let me write the first term first. So when this acts on this, I can write this. Here's a reference sign. This whole thing I can replace by this. So the next task is to get rid of this factor, because you want something like m d2x d tau square. Okay, so how do you get rid of this factor? Just multiply by the inverse matrix, right? So multiply. So this equation, so in the equation, multiply the left, multiply both sides by gamma is a free index. Okay, we multiply by this both sides. Is that clear? And given an equation, I can always multiply by this, and alpha now the mu will be contracted, right? Mu is a repeated index. So this gives you m. So this gives a delta gamma alpha, right? Because mu index is contracted, so you get basically the derivative of x gamma with respect to x alpha, right? That gives you delta alpha gamma. So that converts this alpha index to gamma. Is that clear? Yeah, this part we have to keep as it is. So plus m no, so this is alpha and beta. That's what happens to the left hand side. On the right hand side, we just have to multiply by this. This is equal to E times eta mu nu Is that clear so far? Okay. So now we are going to try to make this into G mu nu. Okay, not replace it by G mu nu, but try to see if we can do some manipulation to make this into G mu nu, because we expect something like G mu nu to come, right, in a covariant form. Okay. So for this, you have to again multiply by an identity matrix. So we will write this as E let me write these things first. And then here, eta mu nu f nu rho, I'm going to write as eta mu tau is not a good idea, mu kappa Okay, I've not really done anything. Once you sum over kappa, this kappa gets replaced by mu. That clear? It's the same expression. But now I'm going to write this. Yeah, I can put alpha. But alpha is not there in this, right? This is delta nu kappa, right? By chain rule, because this will be derivative x prime nu with respect to x prime kappa. So let's put things together. So this is E times I'm just going to order them appropriately. So which ones have gone? So this has gone, this has gone. Eta mu k has gone, and this one has gone. Then you have f prime mu k, mu kappa, mu rho of x prime. So this you have gone. And now that one. And then this. Is this clear? Right, just rearrange these various terms. All of them are gone. You recognize some parts of it? This one, G gamma alpha with upper index, right? So this one is G gamma alpha. Sorry, gamma alpha. Let's look at the left hand side. You recognize what this object is? This will become the Christoffel symbol in the unprimed coordinate system. Right? Because let me remind you, I mean, this we have in fact seen several times before. So gamma, we know its transformation law, right? So we can relate it to, let me put alpha beta gamma is equal to plus something. If this was the only thing, then you should have gamma would have transformed as a tensor. But we know that it's not transformed, it doesn't transform as a tensor, so there is something else here. Okay? So this is general form between any two coordinate system. Okay? But in the local inertial coordinate system, this is 0. Okay? This is 0 in the local inertial form. X coordinate is arbitrary, but x prime we have chosen to be local inertial. So this is 0. So this is the only term that remains. Okay. And the exercise that I'll leave with you is to show that this object that we have here, okay, besides this dx deta term, is exactly what is left behind. Okay. So exercise gamma alpha beta gamma is no, this is fine, I think, because this is times gamma. Just 1 minute. Let me write that. Okay, yeah, true. Yeah. Yeah, this is gamma beta, gamma alpha beta. Okay, and that basically follows from this. Okay, basically this term that is missing is exactly this term. Okay, this if you look at your old notes about transformation of Christoffel symbol, you will find exactly this term over here. Okay. So in a general coordinate system, we can identify this part as a Christoffel symbol. Okay. So we get the equation M X gamma. Equal to alpha
A factor of E also, right?
factor of E also.
E.
Thank you. Yeah, that E. I don't know. We might missed it somewhere. There is a E. Thank you. M in the second term. Thank you. Okay, I'll put like this. Is it clear? Because up to this point, it's just a rewriting of the original equation, right, in this new coordinate system. Now we have to take a call and give it a name. Okay, and we will call this if mu goes there. So f alpha beta, mu is the first one, right? Yeah, alpha beta of x. This is definition. Is this. Because the point is that we had not defined f alpha beta in the general coordinates, right? So it's up to us. If we want to make a new definition, we can give it, right? So we just defined this to be f alpha beta of x, right? But the definition of f alpha beta x is that you first go to the inertial frame, local inertial frame, where you know what f alpha beta are, right? The electric and in terms of electric and magnetic field. And then in a general coordinate system, you use this formula. See? Another way of saying this, you declare that F is a rank 0 to tensor, because this is the way rank 0 to tensor transforms. So you declare that F is rank 0 to tensor. Okay, well, let me again emphasize that it's not something that somebody has given us, right? We are choosing to declare F as a rank 0 to tensor, right? Because we only know how to define F in the local inertial frame based on principle of equivalence. So then it's up to us to define what F is in a general coordinate system. Is that clear? So this then is a nice covariant form of the equation, right? So let me write it once more. So F because ultimately we got back everything that the intuition told us we should get, but I mean, we didn't have to put anything ad hoc, right? We just started with the original equation and then rewrote in this language.
This also and also the relativity possible to write it in covariant in terms of covariant.
Well, sometimes one writes this as capital D, but that's not very illuminating, right? Because the point is X mu is not a tensor, right? So when you say covariant form, right, we have not defined what covariant form means, right? When something is not a tensor, right? For Maxwell's equation, we will see that we can write it in a covariant form, because now that F mu is a tensor, we'll be able to write Maxwell's equation in terms of covariant derivatives, right? But for X mu, it's not clear what it would mean. That's not a tensor field in the standard way, right? Right. So we have only defined covariant derivative of tensor fields. Right? As I said, you can declare this to be something like M and make it look nice, right? But it's, I mean, ultimately you have to define what this D is, right? So that way it's not very helpful. We'll keep the gamma as it is. Okay, but the point is, it is true. I think what you are saying that this is the combination that transforms covariant.
The question that we're asking, how the
Position of a particle doesn't transform covariantly. X becomes some arbitrary function of X prime, right? Yeah.
That's why we can't write.
Yeah. dx d tau does change something like a tensor, but again, I mean, it's not a tensor field, right? The way you have defined tensors, right, it has to be defined everywhere, and then we can transform it. Right? So for this one, we'll just keep it as it is, right? Because we'll not encounter it too many times. So one factor of gamma doesn't really make a difference. Okay, so now that you have introduced F as a rank 0 to tensor, that we will also do something about the vector potential. So F prime mu nu that you know, right? Because this is in the local inertial frame, we have an expression for F like this. The question will be, can we write something similar in a general coordinate system? Okay. And that will require also defining some A mu in a general coordinate system. Okay, it's up to us as to how we define A mu in a general coordinate system. But we can guess from here that the natural way to define A mu will be that it is a rank 0, 1 tensor or a covariant vector, right? That's how we will define A mu. Okay, so we define A mu in a general coordinate system. We call this alpha index because that's what we are using. Coordinate system as E alpha of x
This derivative, if we don't have a covariant derivative here because of this antisymmetric structure, right?
No, it is in a local inertial frame.
Yeah, but this is a covariant definition.
So that will come afterwards, right? Right now, we are just defining it in the local inertial frame, right? So there's no gamma at all. Gamma is just 0. Yeah, then we will start from here and then we will see how to generalize this, right? So we start from here and then we say that if we want, it's up to us how to define as A alpha, right? I'm just giving a procedure. Right? This is I declared that A in a general coordinate system I'll write like this. Okay, and then the question will be, what will be F in terms of A? Is that clear? F prime we know in terms of F prime. Right? This we know F in terms of F prime, right? And we know A in terms of A prime, but we can also reverse it and write A prime in terms of A. So clearly there should be some relation between F and A, right? Because F is a function of F prime is a function of A prime, and A prime is a function of A. Right? So F should be writable in terms of A. So what is that relation? Any guess? Yes. Okay, then let me claim that this is a relation. You believe it? Believe it or don't believe it? You believe it. Why? Okay, can you prove it? It's from? Yeah, so I think what he said is correct, that this is a tensor, right? That we have to use. Okay. So remember, we have one property of the tensor that if all components vanish in one frame, it vanishes in all frames, right? That we had shown, right? So this is a tensor, clearly, right? Because once you have declared that this is a covariant vector, right? This is a tensor, rank 0 to tensor. So let's evaluate this combination. F mu nu minus d mu nu minus d nu mu. What is this in the local inertial frame? It is 0, right? Because if F prime mu nu here, these become ordinary derivatives, right? And in local inertial frame, we have this relation. So this one clearly vanishes in local inertial frame. All components vanish in local inertial frame, right? Because in the prime frame, in local inertial frame, this relation is valid, right? This is what we are defining. So if all components of this tensor vanishes in local inertial frame, then it must be identically 0. Right? This is in fact the reason why tensors are useful. Right? If you want to show that some tensor equation is correct, right? the brute force will be to start from here and keep making transformations, right? That also you can get there, because after all, f can be expressed in terms of f prime, right? F prime can be expressed in terms of a prime, and a prime can be expressed in terms of a. Right? You can follow that route, and you can eventually derive this. Okay? But it's not necessary to do that, because tensors have this nice property that if you can show that a tensor equation, if a tensor vanishes in one frame, it vanishes in all frames. Okay, so that's the way. That's the simple proof that this must be the correct form. Is that clear? But you should be a little careful about applying this. If, for example, you have two covariant derivatives, one after the other, right? Then it cannot be replaced with ordinary derivatives, because the first covariant derivative is okay, right? Gamma you can set equal to 0, but the second one, when it acts on the first one, there is gamma already on the right hand side. So then you cannot conclude that this is 0. So let me say what you are saying. Okay, just as a caution. Okay, it's not relevant for what we have here, but imagine that you have this relation d mu. Suppose you have a relation let me call it some other vector b prime rho equal to 0. Okay, B is a rank 0, 1 tensor. And you want to know what will be the form of this equation in a general coordinate system. Okay, now you may be tempted to say that this will be just replace ordinary derivatives by covariant derivatives. But this is wrong, because this one, right, if you evaluate this in the locally inertial frame, it doesn't reduce to this. Because in locally inertial frame, the gamma that is sitting inside d nu is 0, but the derivative of gamma is not 0. Right? So this is not true. Right? There are corrections to this. Right? And debate as an exercise to find out what exactly is a covariant form of this equation. Okay, this equation doesn't go over to this. Yeah, we have to add something, right? And that something is something that you have to find, right? It doesn't follow just by replacing ordinary derivative by covariant derivative.
This is saying that d nu acting on 0 is not a tensor.
No, it is tensor. This one, it is a tensor. The covariant derivatives by construction are tensors, right? It is not 0. It will be one tensor. Okay, so what you will find is that this is the actual equation is something like this: d mu b rho. Okay, some constant which I don't remember what it is, and then you will have something like r. Okay, I'll not try to say what it is. It's r times b, right? It's a perfectly tensor, but it involves some contraction of the Riemann tensor with b. Right? So the generalization of this to a general coordinate system involves this kind of combination. Okay, so it's not that whenever you say a covariant derivative, whenever you see an equation like this, right, ordinary derivative, you can just replace the ordinary derivative by covariant derivative and declare that that is the correct equation.
So this is happening because in local inertial frame, it is not necessary that second derivatives of
Exactly, that's right. Right. So as long as you have one derivative, it's okay. Right. If you have two derivatives, then you cannot simply replace ordinary derivative by covariant derivative and claim that that is the correct equation. Okay, but here it is okay because you have only one derivative. Exactly. Yeah. Yeah. If you know, if the equation in flat space involves things whose transformation laws you know, right, then you can convert it to a general coordinate system. Otherwise, you have declared transformation laws according to your convenience. Right? If nobody has given you the transformation law from the beginning, right, then it's up to you to say, okay, this is what you define as the object in a general coordinate system. Is it clear? Okay, and now we have one more relation which will be useful later, and this is in fact okay, this follows because the extra terms, right? Let's look at the extra terms. The extra term will be that's from the first term, and from the second term these two terms cancel because gamma is symmetric under the exchange of the two indices. Okay? So that's something special. Okay, because of this antisymmetrization, if you just had d mu nu, then you couldn't have replaced it by this. But in antisymmetric combination like this, you can replace by ordinary derivative. Is it clear?
That should be the same equation as in a gravity.
Yes, exactly. Right? That you go to the inertial frame to write down the equation in absence of gravity, and then you convert it back to a general coordinate system, and that gives you how the equations look in the presence of gravity. And so this particle moving satisfying this equation, right, is under both electromagnetic and gravitational force. Right? Because even if the electromagnetic force was zero, the particle still feels gravitational force, right? That's the effect of this geodesic equation.
Transformation. Also add scalar because
That's a gauge transformation. You can, because gauge transformations don't change anything, right? Well, in this case, everything will go through, but why do you want to make life complicated, right? I mean, the point is.
this is natural because we want to transform like a
Exactly. But in a gauge theory, right? I mean, whenever you transform, you specify a transformation law. You can always add a gauge transformation. Because combination of two transformations, two symmetries is still a symmetry, right? So you can always add a gauge transformation, right? And then mu will not transform as a covariant vector. That will have this additional gauge transformation. But in all physical quantities, it will just drop out. That's why it's more natural to just declare that mu is a covariant vector.
Precisely where did the principle going? Because what we have done is just a coordinate transform.
Yeah, but the starting point was the principle of equivalence. The fact that in the locally inertial frame, there is no additional term.
No curvature dependent.
Exactly. That's why principle of equivalence went in. Right? And in fact, I mean, you could have said, okay, once you have gotten said that the free particle doesn't have curvature dependent term, right? Couldn't have we have used it? Could you have did you have to use principle of equivalence again? Okay. And the point is, you actually are using principle of equivalence again because there could be term that involves product of the Riemann tensor and the F mu on the right hand side, right? Which will be not there for in the absence of electromagnetic field, but which will switch on when both Riemann tensor and F mu are present. So you are using really principle of equivalence at all stages, right? That the fact that the right hand side doesn't contain any extra term, right, that you are using. Exactly, that's right. So the point is in the absence of, so this is not a geodesic. Yeah, if this is zero, then it will be like a geodesic, right? Because in the absence of electromagnetic field, the particles would propagate energy along the geodesic. Exactly. Is it clear?
Is there some general statement about this? Because in this case, we are seeing because of antisymmetry, the extra terms we are getting.
Yeah. General statement, yeah. Basically, the point is things like Carl. I mean, there is a general statement, but probably stating it will be a little more complicated, right? It's it's easier in the language of differential forms, but things like curls.
Because it is exact. Because it's d of something.
Exactly, because it's d of something, right? Then that can be defined without using the metric. That's more a topological definition. Exactly. Right? What is in differential geometry, what is called exterior derivative doesn't really care about the metric, but it still gives a tensor. Just the antisymmetrization basically removes the gamma part. Okay, so now let me turn to Maxwell's equations.
That will be true for any tensor, right? It's a vector field.
Yeah, any
Antisymmetric derivative.
well, if you have a symmetric tensor and if you take a derivative, right, then it's hard to define something like this. Suppose they are a totally antisymmetric tensor, and you take a derivative and then antisymmetrize in all three indices. That will be true there. Because all those are differential forms. Right? So Maxwell's equations, okay, they have two parts. The first part, in fact, just follows from this. Okay? That's what is called the Bianchi identity. Okay, let me write this. Okay, in absence of gravity, when we will introduce gravity. Is this familiar? Well, right now there is no gravity at all. Afterwards, when you apply principle of equivalence, you assume that this is valid in prime coordinate system, right? This is now right now assume there is no gravity. Yeah, otherwise there will be just too many primes floating around. So this one, right? I mean, when mu nu rho or ijk, this just gives divergence of B equal to 0. Okay, and when mu nu rho are 0 GAK, right? One is 0, the other two are spatial. Then this gives curl of E. These are the source free Maxwell equations. And this, the fact that this is true is just a direct consequence of this. This is a consequence of okay, so you are going to first generalize this to Kerr space. Okay. The other ones are a little more complicated because they have sources, right? That I think we'll deal with tomorrow. So in local inner cell frame, so in presence of gravity, now we have in presence of gravity, in local inner cell frame, we have Is clear? So what will be its generalization in a arbitrary frame? Arbitrary coordinate system. Okay. Now we have no choice of redefining f because we have already declared that f is a rank 0 tensor, right? We are not going to change it anymore. So what will be the form of this equation in the general coordinate system? Yeah, just replace the derivatives by covariant derivative, right? D right, and the argument will be that the difference between this, okay, this combination, right, when you evaluate in a local inertial frame is identically 0 because of this equation, because d mu becomes ordinary derivative.
Itself contains some partial derivative. So when we move that to that will also have del del kind of thing. So
Okay, if we are using f as a function of a, then what we are saying is correct, right? But now we are just thinking of this as an equation for f and using the fact that f is a rank 2 tensor. So you have only one derivative, right? Okay, that's how you can do this, right? If we had two derivatives, then we would have been in trouble, right? But we are not writing f in terms of a in this case, right? That will be a separate equation where we saw, in fact, in hindsight, the reason that it is possible is because in this we have actually can drop the gammas, right? So there is no this problem that we discussed earlier, right? That the derivative can act on gamma is not present because f mu doesn't really have a gamma in its definition, right? But just within this argument, right, we are not even using the fact that it's given in terms of a mu. Is it clear? So then this is the form of the Maxwell, that these two source-free Maxwell's equations in the presence of gravity. Okay, and in fact here again you can show that the gamma terms drop out. Okay, when you write it out, okay, the gammas drop out. The exercise is equivalent to and the reason is essentially what we discussed. This combination is totally antisymmetric in mu nu. Exactly. In language of differential form, it will be like df equal to 0, right? Which again doesn't know about gamma. But you can write it in terms of Christoffel symbol and you can show that the gammas just drop out. The other sets of Maxwell's equations are more complicated because they have sources, right? So to understand how those transform, we also have to find out how the source is transformed, right? Because we write the equation in the local inertial frame, right? If we have learned how they transform, right? What about the sources? The sources are not arbitrary variables, right? The sources are determined in terms of particle motion, right? Once you say there are a bunch of particles moving in a certain way, the source can be determined in terms of those. So you have to figure out how the sources are transforming, and then we can generalize it to Carl space. So these I think I'll do tomorrow. Okay, the other two Maxwell's equations. Yeah.
Are you trying to say that that principle is redundant because it is used this derivation.
No, maybe I didn't get. So what do people do normally, you said?
I mean, people use principle of this minimal gravitational coupling, right? That
Yes.
they can just take a
Yeah. So minimal gravitational coupling is the same statement as the principle equivalence is valid.
principle of equivalence.
Is valid. So what people call minimal gravitational coupling, right, is synonymous to principle of equivalence. Okay, you can call it either way. Right? The fact that there is no additional coupling to Riemann tensor, right, is what you mean by minimal gravitational coupling, right? And that's also the claim statement of principle of equivalence.
Principle of minimal coupling, because there are some cases like where some higher spin frequencies they can, I mean, it's necessary for them to non-minimal couple, right? Because otherwise there's some inconsistency.
Yeah, true. I mean, right now we are just discussing based on covariance, right? If you want to judge the covariant equation of motion, you can always get minimal coupling, right? Whether the theory is actually consistent, we don't know, right? I mean, even this we don't know, right? I mean, Maxwell's equation coupled to gravity, it's an interacting theory, it's not renormalizable. Is it a consistent theory? We don't know, right? If you embed it in string theory, you get non-minimal coupling. So from at a deeper level, right, the non-minimal couplings may be necessary for a good quantum theory. Exactly. So once you come into renormalizability and etc., I mean, maybe you have to introduce non-minimal couplings, right? Because we know that gravity, the minimal gravity is not renormalizable.
When you have a torsion tensor, F is not.
Yeah, true. Well, then you have torsion tensor, you have, I mean, okay, you can call it torsion, but it's just a non-minimal coupling. Because gamma mu nu rho, right? You add to gamma mu nu rho as tensor. T mu nu rho, right? T mu nu rho has tensorial properties. So you can write it as gamma, right? Plus a tensorial term, right? And then whether you define whether you include that in the definition of F or not is up to you. Right? The two definitions of F, right? One without the torsion and one with torsion, differ by tensor. Right? All I'm saying is that if you use here in d mu, right, another S mu nu rho, which is this torsion term, you can write this as this plus something which is a tensor.
So you write the Maxwell equations how? Would you write df equals 0 or would you have to modify that with the?
Well, that depends on your theory, right? I mean, if
I see.
I mean, both are consistent with general coordinate invariance, right? Now, if your theory tells us that you should couple torsion within Maxwell's equation, you do that, right? On the other hand, the theory may tell you that the torsion doesn't enter the Maxwell's equation, then you drop it. Both are general coordinate invariant equations. Right? So theories with torsion can be written as theory without torsion by adding an extra tensor.
So when you said that the principle of minimal gravitational coupling is the same as equivalent, minimal gravitational coupling also forbids you from adding
torsion.
Arbitrary terms, not just torsion, but arbitrary terms in the Lagrangian with higher powers of the Ricci.
Exactly. Yeah. So if you
so
add those terms, they'll affect the equation of motion, right? They'll not over principle of equivalence.
But they won't affect the geodesic equation, right?
No, if you add r mu nu to it, dx mu d tau dx nu d tau, right?
Oh, I see.
They'll affect the geodesic equation. So you can certainly add non-minimum terms that will also affect the geodesic equation. Right? I mean, better still, instead of saying that it's normally you get the geodesic equation by varying g mu nu dx mu du dx nu du, right? Add to g mu nu as r mu nu. Take g mu nu plus r mu nu dx mu du dx nu du, right? That will be a different geodesic. Okay.